Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 20. We are in lecture 7, the second part of lecture 7, which is also the second part of our section called simple regression. Okay. Now, it may seem ironic to you that this is called simple regression, but there are more complex regression models which use our multivariate regression. And these use a matrix notation, and so this is simple, relatively speaking, although you may not find the concept that simple yourself at this point. So we did an introduction last time of the concept of least squares regression, correlation. We did a review of what we found in sections 4.2 and 4.3 for correlation and regression. In 4.2, we looked at the special case when the absolute value of rho equals 1. Rho equals -1 or rho equals 1, okay? And then in section 4.3, we looked at the conditional mean of y given xi. Now, this is also, just in case it's confusing to you, the notation, this is the same as, y given capital X equals little xi, okay? So just to say that those are the same. So here we went over the model assumptions. I won't go over those again, but please make sure that you know these and that this makes sense. We talked about the errors being normally distributed and their distribution. And then we talked about an equivalent form of the model. Okay. And so now we're going to talk about the form of the straight line model that we're going to use in this section. This equivalent form of the model, in this textbook, the book uses this for the derivations. Many people use just this form for the derivation. So I'm telling you this so that if you take a course similar to this, maybe in grad school, or take this course years from now as a refresher course like I did, I don't want you to be confused. They may use this formula in one course and use this formula in another course, but remember, they're identical. The only difference is we're making a substitution. Okay? So we're going to use equation 1 here since the book does. So we're going to derive our least squares estimators. Okay? So we have, for the sum of squares, we need to define some notation and some formulas. And so for the data, we have this data, and the data comes in pairs. So for every value of x that we observe, there's a value of y. These things happen together, like height and weight, okay? And so each of these pairs of data are now independent of each other if this is a random sample. So they're independent. And if these pairs are independent, that means if we look at x's as just true values, that the y's are independent even within, let's say this is x1, y1, 1. And so that for every value within x, we're going to say that wherever x1 occurs, we take a sample and we get a bunch of repeats of x1, then we'd have y1, 2, x1, y1, 3, etc. And because these are a random sample, we would see that the y's are independent here. And what we're saying, I just want to make this clear, the book, I don't think it shows this picture, and I found this picture very helpful to me. Whoops, if I could draw a straight line. So let's say we have x1 here. What we're saying with these assumptions is that x1, that the y's at x1 have a normal distribution. Not that I can draw it right. This is y. And so if we held x constant and randomly selected from values of x1, then it has a distribution. Now some of the data sets are small, and so you only have one value from this distribution at x1, which is kind of what we're showing in the top line here. And what I'm showing is that, let's say for some value of x1, we keep on getting values of x1 when we're taking this random sample, and we'll get different values of y. So the first value of y would be here, the second value of y would be here, the third here, etc. And so if this is a distribution and we're randomly sampling from it, all the y values are independent as we're holding x constant. And then if we're looking at this other value of x, let's say call this x2, then all the values of y within that distribution, because we're randomly sampling, they're independent as well. And that would mean that the y values between these two, all these different y values that we've selected, they're independent to the y values in the other distribution as well. Okay, so all the y's are independent. We think of y as the variable and we think of x's as a constant in regression, because we're saying that we can fix or set x in our experiment if we call it an experiment, and then y will vary. As we repeat the experiment, the variation within y for that same value of x, they won't all be the same. They may be very close to each other, but they won't be identical. Okay. So this maybe helps you understand the assumption that the y's are all independent. And we think about this in terms of y, not as in terms of x, because we're saying that the x's are values we can fix or set, so they don't have to be randomly, okay? The x's are not considered random variables in this situation. The x's are considered predictor variables that we can control. Whether that's true or not, that's in the actual situation, that's how it's viewed. We're viewing them as true values that we can measure, and the y values as the variable, okay? So the covariance between x and y, the sample covariance between x and y, sample covariance of x and y, okay? So sample covariance is the distance that xi is from the mean of the x's times the distance that yi is from the mean of the y's. So it's a product of these two errors, if you will, or deviations. Okay? And through algebra, we can simplify that and write it in this form. Now, think about this. If you can do this in this form, then shouldn't you be able to do something similar for this one? Okay. So, yes, it turns out we can do the sum of xi squared minus 1 over n, sum of x's, xi, quantity squared. So here we have two different quantities, but here we could write this as the sum of xi minus x bar times xi minus x bar, right? So we can write it in equivalent format, and we see here we take the first times the second, x times y, or I'm sorry, the first of the first one times the first of the second one, xi times xy, minus 1 over n, the sum of this times the sum of this. So we have xi, that's xi squared, minus 1 over the sum of the first one times the sum of the second one, which is what we have here. Okay, so by pattern, we can show this. This is actually very simple algebra. So to get this, you can expand this portion, xi squared minus 2xi x bar plus x bar squared, distribute the summation, and do a little algebra, and you can get the sum of xi squared minus the sum of xi quantity squared. I want to point out something to you. You're advanced students, so you should know that these two things are not equal. They are not equal. That means you cannot just solve this and substitute in for that. That does not work. You will get the wrong answer. And if I see you doing that, I will take off all the points for that problem, because we're higher level mathematicians and statisticians at this point, and there's absolutely no reason for us not to understand algebra to this state. The only time that this is equal to this is when the xi's are zeros and or ones. Think about that. Positive ones. So if all the values are binary, 0, 1, then yes, these two things are equal because 0 squared is 0 and 1 squared is 1. They're identical. That's the only time that this relationship holds. For any other values of x, it does not hold. So it is not the same thing. If it were the same thing, I would tell you, because then we would only have to calculate the sum of x's, and that would be much easier than calculating the sum of x squared. So x squared, this is how you would do it. If you have negative 1, 0, 1, 2, 3, then you have to square that 1, 0, 1, 4, 9. We add this up, we get 5. We add this up, we get 15. So this is the sum of xi. This is the sum of xi squared. The sum of xi quantity squared equals 5 squared equals 25 is not equal to 15, which is equal to the sum of xi quantity squared. They're not equal, so you cannot use that. All right, enough on that basic algebra, but I do want to remind you of that, so please don't make that mistake on the homework or test. My goodness, please don't make it on the test. Okay. So this is going to equal sum of yi squared minus sum of yi quantity squared. Okay? And this is the sum of squares of y, is sometimes how it's written. This is sometimes written sum of squares x. So different notations depending on the different authors and preferences. So if you write this as SSX or SSX, I'm fine with that. Any of those notations fine. I understand what that means. It's fine to me. Choose one that you like and then stick with it. Okay? So your homework is to show these two things. And I will put that on the homework. So, all right. So you're going to show this, and this is the form of what we did. This is what we did here, but we notice that we did the same thing. It's the same form with the same technique to get to this quantity, and I wrote these wrong. I left out the 1 over n. I apologize. Minus 1 over n, and this one is the same. It's the same pattern, 1 over n. So please make sure that you put that back in. Okay, so if you can show this, you can show these as well. Okay, so that is your first one. The second is something we're going to use in the derivations below. We're going to come up with a quantity, and I want you to be able to show this is true. Now, look at what you're left with. You're left with xi times, you're left with this times this. And something else has to go away. What is it? It's this times this. We're distributing the xi minus x bar, but we're not multiplying it out. So I'm giving you the first step of how to do this. Sum in I equals 1. This is equal to, and we'll have a big bracket here, xi times yi minus y bar minus x bar times yi minus y bar. And then you can distribute the summation, and this you don't mess with. You leave it alone because it's going to be the only thing left. So this, you have to show that the sum of this is 0. Okay? The sum across I of this quantity is 0. So I've given you the hard part of the proof. You get to do the tedious part. Okay. So we're going to give a definition here of a least squares estimator for alpha and beta. And we're going to call it, which is very confusing to you probably, we're going to call it alpha hat and beta hat. Wait a minute, I thought alpha hat was an MLE, and alpha tilde would be an MME, but no. Alpha, the hat, just means an estimator. That's all it means. The context will tell you which it is. So that, to me, can be confusing. I'd rather know. This just means estimate. So that's why you saw me at times using alpha hat MLE for the maximum likelihood. And there's some books who use alpha hat MME for the maximum, the method of moments estimator. This book used a tilde just to show them, because they didn't want to use these subscripts. So here, if I were you, I might write this as LSE for least squares estimator, so then I don't get confused. Because if you just see alpha hat, you shouldn't assume what it is. It's an estimate, but it can be any type of estimator. And so you have to read around to figure out what it is. But if you use nice notation, then you can just glance at it and go, oh yeah, this was the LSE, the least squares estimator. That was the MLE. This is the ME. And then it's easier. All right. So we have this equation, one equation, and we have two unknown parameters. And we want the values of alpha and beta that minimize this error sum of squares. What error sum of squares? Well, okay, let's look at what we've got in here and rewrite this. This is going to be epsilon I squared. Why? This here, I can rewrite this yi minus, and now I factor out a negative, and I have alpha plus beta xi minus x bar, and this is inside the square, right? So this thing's squared. And this is mu of y given xi from before. That's what this equation is. So this is equal to the sum of, so yi minus mu of y given xi is equal to epsilon I. So this is epsilon I squared. So it's the sum of the errors epsilon I squared. And so that's where we're starting. So unfortunately, the book doesn't put this, and we usually go this way and show this, but either the book didn't do that or I forgot, one of the two. So that's what we're doing. We're starting off with the sum of epsilon I squared, which is equal to the sum of yi minus mu of y given xi squared, which is equal to, substitute in for this, sum of yi minus alpha plus beta times xi minus x bar, and then distribute yi minus alpha minus beta times xi minus x bar. Okay, so that's where we're starting here. We've already made these substitutions. Okay, so it's an error sum of squares, and that's where we start. So that means you need to know those other relationships to get to this point. So we're going to start here, and we have two equations, or we have two unknowns. We need two equations. So what we're going to do to get those two equations, we're going to take the derivative of h with respect to the first parameter, set that equal to 0. That will be finding a minimum or a maximum, right? And then we'll take with derivative to the beta, and that gives me another equation which I can set equal to 0 and get either a minimum or a maximum depending on that. Now, we call this least squares estimator because think about this. This is yi minus mu of y given xi, quantity squared. This is a constant at xi. Given xi is fixed. This is a constant. So we're taking y minus, let's say, c, quantity c sub I, squared, yi squared minus 2ci yi plus ci squared. This is the equation of a parabola. Okay? And if there's a the y, so this y has a positive coefficient, +1, not -1. And so this is going to be a parabola somewhere. And so if it's a parabola, when I set the derivative equals to 0, I should get the minimum. So the least, that's why it's called least squares, because we're squaring, we're making a parabola, and then we're taking the derivative setting equal to 0, so we're finding minimums. But it's always wise to check to make sure that something's not off with this, okay? So anyway, so to get alpha, we're going to take h of alpha beta, the partial of that, with respect to alpha. And so remember that the derivative of the sums is equal to the sum of the derivatives. And then once you know that fact, you can expand this by grouping. I can group these two, and now I have f plus g. I can consider that one function. And so I can use the first rule to do the derivative of that. So if I do this, then I have f plus g prime plus h prime equals, and now I use the first rule, f prime plus g prime plus h prime, and I can use induction to prove that this can be extended to an infinite number of sums of derivatives. So the sum of the derivative of the sums is equal to the sum of the derivatives, and the sum of the derivatives is equal to the derivatives of the sum. So that is something you need to know to do calculus, especially in statistics here with all these summations. All right. So I'm going to take the derivative. So this is going to be the sum of d alpha of what's inside yi minus alpha minus beta xi minus x bar quantity squared. Okay? So I can do that. I can't take it inside the square, though. I cannot do that. So this is equal to 2, the sum of 2, times yi minus alpha minus beta times xi minus x bar. And then I reduce this by 1. 2 minus 1 equals 1. Well, anything to the 1 power is just itself. But now don't forget the chain rule, or else you're going to get garbage. So now I have to take the derivative of this with respect to alpha. Not y, not x, alpha. There's only one term that has an alpha there. So I have 0 minus d alpha, or actually I'm going to make this, so d alpha is equal to 1. I have a negative out in front of it, so this is going to be a minus 1, and then minus 0. There's no alphas in this last term. There's no alphas in the first term. And circling that negative made it look like, it was a theta instead of that. So I've got minus 1 minus 0. And this gives me, I can pull the 2 out. I can pull this negative, this is negative 1. I can pull that out, so I end up with negative 2 sum of, and I'll use the square bracket because I have another parenthesis, yi minus alpha minus beta xi minus x bar. And I set that equal to 0. Now this is my first derivative here, okay? I can keep the negative 2 out in the front, and I think I will because I'm going to use it when I check the second derivative. So I'm going to pull that out, and then I can distribute the summation, so sum of yi minus the sum of alpha minus the sum of beta times xi minus x bar. Okay. I could divide both sides by 0, get rid of the negative 2, but there's really no need to do that. You can leave it out there if you want. Now, this is, zoom in, I equals 1 to n. So there's alpha plus alpha plus alpha. There's n of these. And so alpha plus itself n times is n times alpha. It's a constant, and there's no sub I, there's no subscript, and we're using, let me write this a little clearer. Oops, wrong one. We're using I. So since it's the same for every value of I, this doesn't change. So we are summing this n times itself, so n alpha. So that's how we can evaluate those. I hope you learn that method, technique, trick, whatever you want to call it. All right, negative 2. Now I have the sum of yi minus n times alpha minus, I can pull the beta out in the front. I've got beta times, the sum of xi minus x bar quantity. Now, this is 0. It's always 0. The sum of the x's minus their means is 0. Let me show it to you very quickly. Sum of xi minus x bar equals sum of xi minus sum of x bar. X bar doesn't have a subscript I. I'm doing this from I equals 1 to n, so it's going to equal the sum of xi minus n times x bar. N times x bar is equal to this. N times x bar, 1 over n, sum of xi. The n's cancel. So I'm left with this is equal to the sum of xi minus the sum of xi. That's 0. Something minus itself is always 0. Okay? So this term is 0. Okay. So this is equal to negative 2. Don't forget the negative out here. Negative 2. Need to write that. Negative 2. Sum of yi minus n alpha. Okay. This is the derivative. Now I can set that equal to 0 and solve for alpha. So I'm going to divide both sides by negative 2, which gives me the sum of yi minus n alpha equals 0. So that's what I did. I didn't divide by 0 there. I divided by negative 2. But I'm going to get rid of that because I want to keep this as my equation for the derivative. When I take the second derivative, this is simplified, very simple, it's very easy. Or I use it for the first derivative test. This is the form you want for your first derivative. Simplified as much as possible, so much easier to use. Okay, so this implies I can add n alpha to both sides. Sum of yi equals n alpha, and you can rewrite this, right? You can reorder it as n alpha equals sum of yi if you'd like to. I do. I'm going to divide both sides by n, and the n's cancel, giving me alpha equals 1 over n sum of yi equals y bar. So now I check. So I can either use the first derivative test or I can use the second derivative test. I'm going to use the second derivative test with respect to alpha, and I get the negative 2 out in the front as a constant. Y doesn't have any, the yi's don't have any alpha, so those are 0, minus n times the derivative of alpha with respect to itself is going to be minus n, equals 2n, which is always positive, because 2 is positive now. This negative and this negative cancel. N is always greater than or equal to 1. That's a sample size, so it has to be in this case. Okay? Which implies that H is concave up. And if it's concave up, it's curving up, that means when I find the derivative and set it equal to 0, it's got to be a minimum. Therefore, alpha hat equals y bar minimizes H. Therefore, that's a sloppy therefore, isn't it? Triangle. Therefore, alpha hat LSE equals y bar, the least squares estimate. Now, we're going to be using a system of equations. When I have, what did I say? Y is equal to 3x minus 2, and I've got y is equal to negative 4x plus 5. So in order to solve these I need two equations. It's a system of equations. The solutions of one variable is dependent upon the solution of the other. Let me show you. So this is equal to y, this is equal to y, so I can set them equal to each other. 3x minus 2 equals negative 4x plus 5. So I add 4x to both sides. I get 7x minus 2 equals 5. I add 2 to both sides. I get 7x equals 7, and then x is equal to 1. Now to solve for y, I can't solve for y unless I substitute x back into one of the equations. Y equals 3 times 1 minus 2 equals 1. I can use the second equation. Y equals negative 4 times 1 plus 5 equals negative 4 plus 5 equals 1. Okay? So I can't solve the second without the first. So I've now solved the first relationship, which is alpha. And when I get to beta, when I start deriving beta, derivation of beta, I'm going to move this up so I have plenty of room. So beta hat. So now when I do that, at some point I'm going to substitute for alpha. I'm going to substitute y bar. But I'll be very careful with the notation so I don't confuse anyone. Alpha, beta, with respect to beta, is equal to, this is the partial, this is going to be the sum of the partial with respect to beta of yi minus alpha minus beta times xi minus x bar quantity squared. Okay? So the sum of the derivatives is the derivative of the sums is the sum of the derivatives, so I can pull the derivative in here, but again, I can't take it inside the square. I cannot do that. So this is equal to 2, I'll just go ahead and pull that out front, 2 times, and we'll keep the brackets, yi minus alpha minus beta times xi minus x bar, bracket, and then I have to use the chain rule. And so I have to take the derivative of this quantity with respect to beta. So that's going to give me 0 minus 0 minus, this is now a constant with respect to beta, so it's going to be there, xi minus x bar, and then the derivative of beta with respect to itself is just 1. So don't forget the chain rule. So this is equal to 0 minus 0 is 0, but then I have minus here, so I'm going to pull that out to the front, negative 2, sum of yi minus alpha minus beta xi minus x bar, and then xi minus x bar. And I'm going to move this to the front here, and so I get equals negative 2, sum of xi minus x bar times yi minus alpha minus beta times xi minus x bar. And now I'm going to say, I'm going to substitute in alpha hat equals y bar. So to not be confusing, I'm now going to say the partial of h of alpha hat beta hat with respect to, this is squared, beta squared hat is going to equal negative 2 sum of xi minus x bar quantity yi minus alpha hat, which is y bar, minus beta hat xi minus x bar. Okay? And I want to set that equal to 0. So what I'm going to do, though, is now that I have yi minus y bar, that's nice because I have xi minus x bar here, I'm going to group these together. And so this is one term, and this is another term. That makes it a lot easier for me because this becomes negative 2 sum of xi minus x bar times yi minus y bar, big bracket, minus beta hat xi minus x bar quantity squared. because I'm distributing this to here and to there. And this is a beta hat. Okay? And so then I can distribute my summation, sum of xi minus x bar, yi minus y bar, minus sum beta. I'm going to pull the beta hat out in front. It doesn't have an I, so beta hat, sum of xi minus x bar quantity squared. This is equal to 0. I'm setting the derivative equal to 0. Well, this is not this. I'm sorry, I wrote this as a 2, but it's not a 2, is it? It's just the first derivative. Partial beta hat. Okay, not the second derivative, the first derivative. Okay. And now, negative 2 can never be equal to 0, right? So this term is the one that has to be equal to 0. If this is 0, then 0 times negative 2 is 0. So I'm going to solve this and set this equal to 0. This implies that the sum of xi minus x bar times yi minus y bar minus beta hat sum of xi minus x bar quantity squared equals 0, which implies I just add this to both sides and then put it in the front. So I'm going to flip the equation. So I have beta hat sum of xi minus x bar quantity squared equals sum of xi minus x bar times yi minus y bar. Solve for beta hat by dividing both sides by this quantity. I get beta hat equals the sum of xi minus x bar yi minus y bar over the sum of xi minus x bar quantity squared. So this is equal to, is it SSXY? So it's equal to SSXY, this. And then this is SSX, or SXX, or SYY. Okay, so let's do the substitutions in as we can here. So this is equal to SXY, sum of squares of xy, and this is SXX. So that's another way to write this formula, okay? The sum of squares. Now, I can write this, so these are the sum of squares, not the standard deviations or variances, okay? So it's not s squared. It is n minus 1 s of x squared, the standard deviation of x, okay? So you can use that. This is equal to s of xy over n minus 1 s of x quantity squared, the standard deviation of x squared. All right, so our summary now, partial beta, nope, partial h, partial h squared, partial beta hat squared equals, I'm going to come up here to where I said my first derivative was. Where did I? Okay, so I thought I had identified this as my first derivative someplace that I wanted to. That must have been the last time. Okay, so here is my first derivative. So this is going to be partial beta times negative 2 sum of xi minus x bar yi minus y bar minus beta hat xi minus x bar quantity squared. Okay, and I will let you do that because to do this you need to prove, easily do this, you need to prove this property right here, property number 2. So you can use this property in there to do that, but I won't take up more of your time on the video to do that. But this is going to be partial of h with respect to beta is going to be greater than 0, implying that beta hat minimizes h. Okay? And we will stop here, and this is a good place to pick up next time with this example. All right. So please, if you have questions, come to virtual office hours. I'm happy to give you hints and to coach you and lead you through to get the right answer. If you need help before office hours, then by all means email me. If you email me a question about a problem, then you need to email me a picture of the problem, because I do not have them all memorized, and a picture of your work so far, or your ideas. If you just email me and say, I don't know how to do this, I can't help you. That'll be your ideas, okay, of how to do it. I'm planning on doing this. And if you're in the right track, I'll confirm it. If you're not in the right track, or if there's some nuance, I might point you in the right direction for that. Please take care of yourself. Stay safe, because we want to see you here next time.